Hello, in this video I will be describing the HNMR for two different molecules. The first one will be ethanol, and then the second one will be aspirin, which will come later in the video. So here we have the structure of ethanol and then the proton NMR for ethanol. So based on the structure of ethanol, we can see that there will be three signals. Given that the three hydrogens to the left here are going to be equivalent, the two in the middle are also going to be equivalent, so they will produce another signal, and then the hydrogen attached to the oxygen here will produce its own signal, so the third signal. The position of these signals is based on their chemical environment, so basically where the hydrogens are relative to the other groups in the molecule. It's also related to the applied magnetic field, which is generated when you are taking the HNMR spectra. Another thing that also affects the position of the signals is called shielding and deshielding, which is basically when also related to the chemical environment. So it's said to be shielded if the nuclei is relatively electron rich, so that means that the effect of the applied magnetic field is counteracted a little bit by the magnetic field generated by the valence electrons. A shielded nuclei will appear at a lower frequency on the HNMR, so more upfield, so lower frequencies are to the right and then higher frequencies are to the left, and the left is said to be more downfield. So if the atom is electron poor, then it's going to be deshielded, meaning the generated magnetic field is going to be going in the same direction as the applied magnetic field. So deshielded nuclei will then have a higher frequency and they will be more downfield, like these two signals over here. For ethanol, the three hydrogens on the left here produce the signal the furthest right on the HNMR spectra over here. Then the two hydrogens attached to the middle carbon will generate the signal just past 3.5 ppm. So this one right here, you can't really see the difference between these two, but these four peaks here in this one signal correspond to one signal, and then this one peak corresponds to another signal. So then this signal corresponds to these two hydrogens, and then the signal just past that one corresponds to this hydrogen. The integration of HNMR is given by the numbers just above each signal and tells us the number of hydrogens present that generated that signal. As we can see for ethanol, three hydrogens generated the signal on the right, which corresponds to these three hydrogens. And then for this signal, it is generated by two hydrogens, which correspond to these two hydrogens, like I said before. And then the leftmost signal has an integration number of 1, which corresponds to the one hydrogen that generates that signal. The number of peaks in each signal is brought on by a phenomenon called spin-spin coupling, which tells us the number of hydrogens that are present in the neighboring nucleus. So the number of peaks follows the pattern of n+1 hydrogens. So a signal with 3 peaks in it means that the neighboring nuclei has 2 hydrogens. For example, this signal has 3 peaks in it, which means it's a triplet, meaning that n+1 generated this signal, so the number of hydrogens is going to be 2 in the neighboring nucleus, which does follow the pattern that these two are the neighbor of these, and there are 2 of them. And then for this signal, it's a quartet because there are 4 peaks in that signal, which corresponds to these 3 hydrogens in the neighboring nucleus. And then, that just follows that pattern. So that is everything you really need need to know about the HNMR spectra for ethanol. It's quite a simple compound, so it's a nice one to start with to learn the basics about HNMR and how to go step by step through the spectra to come up with the molecule. Okay, so now here we have the structure and the HNMR spectrum for aspirin. It is also known as 2-acetooxybenzoic acid and has the formula C9H8O. So here for aspirin we can see that there are 5 signals on the HNMR spectrum. I've labeled them A through E, and there are 8 hydrogens in this compound, so obviously we know that there are going to be some equivalent hydrogens. We're going to start with these ones over here. So these 3 are going to be equivalent because they are in the same chemical environment. And then this one over here is obviously going to generate its own signal. It's only 1 hydrogen. And then these 4 in this ring are going to generate 3 signals. So this one is going to generate its own, this one's going to generate its own, and then these 2 are equivalent, so they are going to generate their own. It may be slightly confusing to know why these 4 aren't generating the same signal, but it is because of these 2's proximity to the other functional groups in the compound. So and because there are these oxygens present, it's going to pull the electrons away from those nuclei, which is going to push them further downfield, as we know, as we explained in the previous spectrum of ethanol. So, like I said, these 2 are going to be equivalent, and then this one's going to generate its own, and this one's going to generate its own. Now, just looking at the spectrum, we'll start with A. So A corresponds to this hydrogen that's attached directly to the oxygen. So because we know that when the closer that a hydrogen is to an electronegative atom, the further downfield it's going to be. So obviously with this hydrogen being attached directly to the oxygen is going to be quite far downfield. So it corresponds to this signal over here. This is quite typical for a carboxylic acid. So you're always going to see a small short peak around 11. Which is a pretty good indicator for any type of compound that contains a carboxylic acid. You're always going to see this small peak right here. And then moving on, we'll go to B on the spectrum. So B is going to correspond to this hydrogen right here due to its proximity to this oxygen. It's pulling the electrons away from this nuclei, so which pushes it further downfield because it is more de-shielded, like I mentioned before in the spectrum for ethanol. And then so C, because it is roughly the same, these all 3 of these signals are quite close together just because they are in approximately the same chemical environment, being in this aromatic ring. You are also typically going to see signals in a benzene ring such as this are going to be always around 7 to 8 ppm, so which is why we see these multiplets here. So like I said, this one corresponds to B, and then this hydrogen over here corresponds to C, so it is just slightly further upfield than B, just because it is a little bit further away from the oxygens in terms of like counting the atoms away from it. So we have 1, 2, 3, and then 1, 2, 3 away from the oxygen, and this one is just 2 away, which is why it's going to be further downfield. And then these 2 hydrogens are going to be equivalent, and they correspond to the signal here at D. Just because they are slightly more upfield, just because they are further away from the oxygens, so they don't get their electrons pulled away as much as the other 2. And then lastly, we have these 3 over here, which are equivalent, and they correspond to this signal right here. Generally speaking, if we have like an aliphatic compound such as this, like this hydrogen, just because it isn't in a ring, it's going to be generally around 1, but just due to the proximity to the oxygens here, it is slightly further downfield. So, which is why we see it around 2.2, 2.3-ish ppm. Then for the integration for this compound, it's not labeled on this spectra, but we can kind of make an inference based on the relative heights of the signals. So E here corresponds to these 3 hydrogens, like I mentioned before, and which makes sense, it being the tallest peak, or it being the tallest signal because it corresponds to 3 hydrogens. And then here, B, C, and D, we can see on the zoomed in version, this signal D is slightly higher because it corresponds to 2 hydrogens, and then B and C are about the same height because they both correspond to 1 hydrogen and 1 hydrogen here. And then A is also another short peak because it corresponds to 1 hydrogen here. And then also we see these, in the zoomed in version, there are many different peaks in these signals. This is due to a phenomenon called spin-spin coupling, which I mentioned before with the spectrum for ethanol. Basically, there are some peaks due to the neighboring hydrogens. So this peak should be a doublet, but as we can see, there are many different peaks in this signal. This is due to the spin-spin coupling. So these hydrogens will couple with each other, which generates more peaks in the signal, and which is why we see, especially in a ring like this, we see many multiplets in series, which is another way of identifying a benzene ring. You will have many multiplets in series like this. So that is why we see all of these littler peaks in each signal, is because of both the neighboring hydrogens, how many in there, and then also the spin-spin coupling between the different equivalent groups. Obviously here, this hydrogen does not have any neighboring hydrogens, so it's going to be a singlet. And then this one over here is also going to be a singlet because it does not have any neighboring hydrogens here on this carbon. But then these ones obviously will have their different peaks because they have neighboring hydrogens. That is basically everything you need to know about this spectrum as well. I hope you enjoyed this video. Thank you.